Hi, my name is Dean Guramanis. This is video number 3 on September 21st for HackadayPrize 2015. I have 10 minutes, so I'll start off talking about some of the market-ready products I have today, and then I'll get into some of these prototypes that I've made over the years and explain how I used PowerPeg to solve a problem and what each circuit actually does. Here we have the TCAP 4325 thermal connector. The idea of PowerPeg system is that there's a wide selection of interchangeable parts. So in theory, there will be 20 connectors similar to this that have different size input interface. This here is the input interface. This topmost surface, it's 2.5 millimeters in diameter in this case, but different connectors would be different sizes depending on what size chip you want to connect to. But this is where heat enters the connector. So there will be a circuit board where all these things get attached, but the general idea is that the thermal connector attaches to the SMT package directly through a hole and just solders directly to the chip like this. On the bottom side of the circuit board, you would see this, and that's where the heatsink gets attached. Here's an example of a circuit board with the PowerPeg extending from the back, and here's the chip that it connects to. I'll cover more about the input and output interfaces and some design considerations in a next section. But I just wanted to show how nice this one is. This is they're made of copper. It's plated in 99.99% pure 24 karat gold. That prevents oxidation and makes sure you have a consistent connection. This design provides a really low resistance connection between the chip and the heatsink. Finally, we packaged it in this anti-static 12mm carrier tape. This is a standard size from CPAC, and it fits into all of the pick-and-place machines. Next up is the GP43A heatsink. This was the first heatsink that I made to match the PowerPegs. They're made of 6061 aluminum and plated with mid-phosphorus nickel. They have a beautiful shine. I produced about 400 of these in my garage, very slowly, very carefully. So these are handmade heat sinks, and they work really well. So here's the top of the heat sink. This is where the air fins are, because what's happening is heat is generated by this chip. It's transferred through the connector to this aluminum mass. The heat travels up into the air fins and ultimately transfers into the air. With thermal management systems, in the beginning, it's really hard to imagine how the heat is exiting. Some wisdom is that the chain is only as strong as the weakest link. You can provide a really effective heat path from the chip, but unless the heat has somewhere to go, the whole thing is just going to end up heating up after about an hour. So with a heat sink, it's all about the air fins. You want to take the heat and spread it out into the largest possible area for the largest exposure to air, and the heat will travel into the air, and then the air will circulate away from the heat sink, removing heat from the system. So if natural convection is not enough, the GP43A features these 4 080 tapped holes for connection to a 13mm cooling fan. Here's the most recent addition to the selection of interchangeable parts. This is the WC43A, stands for Water Cooler 43 Series A, because it's the first one that I made. This is what the main body of the water cooler looks like. Fluid enters here, circulates through this clover shape, and then exits here. And this large aluminum block acts as a thermal reservoir. In other words, it's a mass with high specific heat or heat capacity that absorbs the heat and transfers it into the water which is flowing through the block. And here's what a motor controller looks like if you remove the GP43A and substitute it with a WC43A. Now keep in mind, just because the heatsink is higher capacity, that doesn't mean the chip is going to be producing 10 watts. You can also add a water cooler to decrease the operating temperature. So let's say that this small driver is driving a really big motor and it's just running too hot. For example, 70 degrees Celsius is like right on the threshold of safety. It's hot enough to burn you if you touch it, but it's not, too ridiculously hot. It's enough to make you feel uncomfortable. So you can bolt on the WC43A and bring your temperature basically down to room temperature. This was the first circuit board ever to use a PowerPeg thermal connector. I described the story of how 10 Products got its start and how PowerPeg was invented in 2011. This is a board done by Avian Electronics. It's a stepper motor driver for DIY CNC machines. It uses the DRV8818, and with this large extruded heatsink that we made, the performance basically tripled. After that, I wanted to design a more miniaturized circuit, which leveraged PowerPeg to make the circuit more powerful, more efficient, and also much smaller. So this one on the left is the first circuit I designed. It's just a very basic breakout board for the DRV8818, and it required a lot of external processing in order to drive the chip. So then after 6 revisions, I ended up coming up with the stepper stack, which is actually another product at 10 Products Inc. It uses the DRV8818 in combination with the C8051 F370 microcontroller by Silicon Labs. I've also done a lot of work with LEDs. The Cree XML LED is a really powerful SMT LED. It just happens to have a 2.5 millimeter output, so it was perfect for the connectors that I had in stock. And I designed a lot of circuit boards with this LED. This one pretty interesting. I used the single Cree XML breakout board here, connected to a GP43A, and on the other side, I actually have a constant current driver chip, also using a GP43A for cooling. They have this special chip, and it's a solid state LED driver. The thing that's so special about it is it doesn't require any transformers or large capacitors. The circuit you see here in all 3 of these boards will take 120 volts AC from the main line and produce a constant current power supply. Another LED light prototype that I made. This was a different approach to taking AC mains and driving LEDs. I hope I did a good job at conveying what you can do with PowerPeg thermal connectors. There are millions of amazing integrated circuits on the market today, and they all sort of share the same challenge when it comes to thermal management. How do I connect to this extremely small heat source, and how do I solder to it easily while still providing good cooling? So PowerPeg is a 2-part system. It makes it simple, and it opens up a huge realm of possibilities and future development. So right now we have this one thermal connector in stock. I plan to have at least 5 more thermal connectors in stock by December, and as far as the heat sinks and coolers, I plan to get more elaborate. We have this water cooler now. I want to start getting into pumps and try to supply miniaturized pumps for stuff like this. So stay tuned, and I encourage you to please consider PowerPeg in your design. If you have any questions, a lot of information is available on the website. It's www.tem-products.com. Please feel free to contact me. My email address is info@tem-products.com. I'll be happy to help. Thanks, and good luck to all the competitors.